This is CPE 233, Lecture 25. This is the introduction to the timer counter module, which is essentially an external module that we are going to include with our RISC-V at the wrapper level. And this is going to do some really important work for us. It's going to open up many possibilities. And so this is important because timer counters are very popular in all microcontrollers, as you'll see. I'll mention that a little bit more later. So this is once again experiment 9. Out there in the real world, and particularly embedded systems, oftentimes you want to prove that your hardware is working. So in software land, when you're writing programs, there was the classic Hello World program to just ensure that you could, write a program and have it do something. Well, blinking an LED is analogous to that Hello World problem for embedded systems. So embedded systems, if you can successfully blink an LED, then you've proven that the tool chain and everything is working and your hardware is working. And so that's why it's important. Very simple, but very important at the same time. So when you're blinking an LED, you have two possibilities. You can blink it at a given rate, and you can blink it with a given duty cycle. And so we will discuss a couple of those coming up later. Okay, so in using a microcontroller to blink an LED, you have two approaches. You could have the microcontroller do all the work, which means it has to put in dumb delays, which is just code that's doing nothing, waiting for the the proper period or duty cycle, etc., etc. The problem with this using dumb loops is if you're using your microcontroller to time the blinking LED, that means you're tying up your microcontroller. Your microcontroller can't go out and do more important things. So the better approach is to use an external device, external peripheral, and the idea here is I'm going to tell the peripheral what to do, and then the microcontroller is going to go back to doing more important things. When that peripheral is done doing what I want it to do, it's essentially going to tell the microcontroller it's done, and it tells it, generally speaking, using an interrupt, and that's the most efficient way to do it as far as embedded systems go in the context of response time. So we're going to connect something. This timer counter is going to connect directly to our interrupt, which is going to do some cool stuff for us. So the things you need to do typically with a timer counter module is timing and counting, or no shock there. Anyway, so essentially with periodic timing, you may be doing stuff like synthesizing periodic signals, like check a sensor every 10 milliseconds or something like that. You may be working with pulse width modulation, in that you have a blinking LED, but you're changing the duty cycle. And of course, these are all nice thing here is blinking LED. But keep in mind when you're talking about pulse width modulation, it's a way to transfer information. Stepper motors work typically with pulse width modulation. The other thing you can do is down here is count things. So you can count the number of times. Depending on how you hook it up, you can count the number of times an event happened, or more importantly, you can, if you have two events happening like this, you can actually use the counterpart to measure whatever this time interval is right here. And so it's a very useful thing for timing and counting. This experiment, we will only be using the timing part. Okay, timer counters, they're very common in microcontrollers. Even very simple microcontrollers have a lot of timer counters on them. That means separate timer counters. Now there's separate timer counters, and there's a bunch of them essentially because they're so amazingly useful. So they can do a whole bunch of different things. Generally speaking, in a microcontroller off the shelf, they have large feature sets of what these timer counters can do. What we're going to do in this experiment is very simple. It just barely does anything, which is good for us because it is simple. And typically, once again, these timer counters are so useful because they're typically an embedded system. There are so many different things that we want to be doing in the background and have the microcontroller go off do more important stuff. So as with many peripherals, particularly internal peripherals to microcontrollers, these things are they're programmable, and you essentially program them by writing to control registers within the object itself. Okay, so that means typically when you initialize your program, you're going to initialize your peripheral, or you can actually change, reprogram it somewhere in your code as well. So this is the timer counter module here. What we have here is a clock in here, a couple inputs and a couple outputs. So what we're looking at here is this output here, and what it's going to do is occasionally generate a pulse, and what it's going to do is generate a pulse when this timer counter reaches a maximum value. So this timer counter, it starts off at 0, it counts upward until it hits this value here that you've preset in that thing, and then it's going to generate this pulse on the output. Okay, and the other thing we have here is this control and status register. CSR is quite important out there. You've seen it before, control and status register. So once again, what we have here is this is the terminal count register, and what this timer counter, the timer is going to count upwards until it hits the terminal count. Once it hits the terminal count, it's going to generate this pulse. It's going to clear the counter and automatically start counting back up again. So once you program this thing, and then you have to turn it on via this control and status register, it works kind of open loop. You don't have to worry about it anymore. You don't have to go reprogram it. So here's the example of how this thing is working here, so that if the terminal count is right here, once I hit that terminal count, you can see my counter counting upwards, blah blah blah. Once it hits that terminal count, it's going to clear the counter and send out this pulse right here. This pulse is this thing is programmed to be 3 clock cycles long. It's actually, you can configure it any way you want. Currently it's programmed at, I think it defaults to 3. If in doubt, go check the code out on this thing. So once again, this is the count register. It's actually the count register. When that count register hits the terminal count, which is this, it sends out a pulse. That's all it does. And so this is going to give me the ability to set this terminal count value to have it output pulses at different frequencies. So there's 2 issues here. There's the timer, and then there's the counter part of it. And so we'll go over the count. We'll go over the timer first. So once again, there's a register in here, which is inside this thing, which holds we'll just say the terminal count, and then there's a CSR register. But there's also another register, which is essentially just the count register. So it is a counter. It is operating kind of open loop in that it's always counting, but when this counter equals the terminal count, that's when it sends out this signal on this. Okay, once that happens, it clears the counter and starts counting up again automatically. Now the counter part of it is right here. Now this is a readable register. So once again, if I wanted to if I wanted to figure out what this value is right here, what I do is set the counter there, have it count, check the counter again at this time, so then the width of this interval here is going to be this value subtracted from that value. So this count value subtracted from that count value. So once again, we're not going to use that in this experiment, but it is a very useful item. So there are 2 registers inside the control, inside the timer counter. One of them being the control status register, and the other one being the actual count. It's the terminal count. There's actually 3 registers. The other register is the count. So once again, we have the count, the terminal count, and this control register. So this control register is what this slide is supposed to be about here. It does 2 things. One, it turns on and off the timer counter. So this is a bit. You have to set this bit to equal to 1 if you want this to actually count. When it's set equal to 0, it doesn't count. The other thing is this clock prescaler here. So I put that in there. Just it's actually an artifact from when we were working with 8-bit microcontrollers. It gave the ability to create a bigger count, but I left it in there simply because many real actual microcontrollers off the shelf have prescalers in them, and I'll show you what that means in a later slide. So to get this timer counter to work, very least you have to do is turn it on, and you can also employ this prescaler also if that helps your project. So the prescaler. So I'll say this is the counter inside the timer counter, and there is a prescale module. So what we have here is a clock coming into it, and we'll say clock 1 and clock 2, and a clock coming out of it, and it's this this clock here, this prescaled clock that actually feeds the counter itself. So the output of this thing would be, I forgot the name of it, but go look at that. This would be TCCNT OUT. Okay, so that's what's going on here. Remember, this is the counter itself inside of this object. So this is also, turns out, what I'm going to do is put those 4 prescale bits into this thing, and it's going to do something with it. So what we have here is a waveform. Make it look like this. This is CLK, clock 1. This is clock 2, and we'll say PS equals 0. So if you set this thing equal to 0, it doesn't do any prescaling. We will say PS equals 0001. That means it's going to do some prescaling here, and it looks like this. Okay, so this, when I prescale it, when I set the prescaler to 1, it essentially cuts the frequency in half. And I'll do one more in this one, clock 2. Looks like I ran out of stuff right there. And you can see that these are equal to this. Okay, so essentially this is PS equal 0010. Okay, so this one, you can see this clock, when PS is equal to 1, it kind of throws out 1 clock cycle here. When PS is equal to 2, it throws out 2 clock cycles. So this is actually missing 2 clock cycles in here. And so that's what the prescaler does. It just operates on the incoming clock frequency and kind of tosses out pulses. So to get this thing to work and to prove that it works, typically you write some kind of driver program. And so this is I'm going to describe the driver program for the timer counter module. So keep in mind that I'm providing you with the driver program and with the module, so you don't have to do anything except you have to get that thing worked into your wrapper level. So eventually when you're going to grab the timer counter module, put it in your project, and put it into the wrapper level. So the driver program has a sample wrapper, but then there's also the generic wrapper we've been using for our RISC-V. They're not quite the same. You're going to have to look at them and make them the same. So this program, what it does 2 things. It blinks LED 7, which is the 8th LED from the left, and it reads the lower 4 switches and outputs the value of those switches to the LEDs. It doesn't do anything to them. So it looks like that if I turn a switch on, the corresponding LED turns on. That's just for the lower 4 switch values. So this is it's definitely an interrupt-driven program. These interrupt-driven programs are always configured to be the same. you initialize something typically, and this program is a great example, you have to get the timer counter set up to work as you want and eventually turned on. But then there's also the background task and the foreground task. So the background task is what it's always doing if it's not getting an interrupt. Foreground task is what it does when it gets an interrupt, and we'll see that in a second. So this is a majority of the code. It's not a long program, but this is the setup code for, this is the initialization code, which every program should have. So got to get the processor in a known state, including its peripherals, and that's what we see here. So first thing here, you've seen this a bunch of times. I'm just loading the vector address of the interrupt service routine. Here I'm just loading some values of I/O ports into registers. So you've seen these two before, which is just the switches and the LEDs, but the two new ones are associated with the timer counter, which is the status register and the terminal count register. And so I forgot, it's this one, counter count port, whatever. This is the terminal count one, and this is the CSR. Okay, you can see that in the wrapper code provided with the driver program. Next thing I want to do here is I am going to be blinking LEDs and doing other stuff with LEDs here. I am going to reserve a register specifically for LEDs, which I'm just arbitrarily going to call it X31. Okay, and so next thing here is, right here, these two lines here, is I'm setting up the timer counter. I'm initializing the timer counter. So the two things here, I have to write two registers, which is the terminal count register, and then I have to write the control and status register, which you'll see in a second here. So arbitrarily I'm setting this to FFFF, which is slow enough, I believe, hopefully anyway, just so you can see the light blink. Remember, this is the terminal count. It's going to start at 0, count up to FFFF. When it hits FFFF, it's going to turn the it's going to toggle the LED. So the other thing here is I'm going to write the control and status register. The only thing I need to do here is turn it on, and it just so happens for this program I'm not going to use the prescaler in this program. Not a big deal. I'm choosing not to. And last thing here is I'm ready to go. End of initialization. Typically the end of all initialization is to enable the interrupts. I am sticking a 1 in a register forevermore because it's so useful. Now the other part of the program is the main code, which is the background task, and then the interrupt service routine, which is the foreground task. So we'll look at the foreground task here, and all it's going to do is it's going to be toggling a bit in X31. If you remember, X31 is a register I'm going to use to keep track of what the LEDs are doing. So what this code does is just exclusive ORs that particular bit. Here's my bit mask. That bit, you know, the 8th bit from the right. It toggles that bit. That's what the XOR is doing, and then it's going to return. So this is my interrupt service routine. What I'm going to do is configure, hook it up so that when the timer counter times out, it's going to be connected to interrupt. When it times out, it's going to generate a pulse, which is going to cause it to go into an interrupt cycle, etc., and then act on it. So what's going to happen in the main code, it's actually kind of chunky here, is I'm going to read the switches and mask the lower 4 bits, which is this code right here. All I'm interested in is lower 4 switches, none of the other switches, so I don't want to deal with them. Here what I'm doing here is this line. I'm taking the value in X31, which is the current value of the LED that's blinking, and I'm ORing it with the X31, which is the register that's holding the LEDs that are turned on. Okay, so once I have all that information, I'm writing it out to the LEDs, and life is good. So the other chunky part here is I'm going to enable the interrupts. Now X8 was already set. This is turning the interrupt enable on. Quite frankly, there's probably a better way to do this code, but this is the simplest. The problem with this code is every time through the code it enables interrupts, even though most of the time the interrupts are already enabled. Other ways to do this, you could say, hey, it's wasting time, but the whole program's kind of wasting time. This is this giant polling loop anyway, not overly efficient. So the program, what you want to do, once again, is you can see it in there. You're initializing stuff, which means you're setting some counter values. You're setting the prescale, configuring the interrupts. Those are 3 tasks in there, certainly not in that order. The background task is going to be pulling the switches and writing to the LEDs, and the foreground task, which is the ISR, is simply going to be toggling 1 bit in that LED register, which is, I think we had it as X31. So it's a very simple program. It's really key that you understand it before you move on this. So the timer counter, once again, there's in the lab manual, there's a user guide in the back of the manual. It sort of describes it in this experiment, but not too in depth. There's a driver program. I think it's on Canvas. It's a .s file. And then there's the timer counter modules themselves. It's actually in System Verilog. So experiment 9, you're only going to do part C, but it is a redo of experiment 8. So what that means is in experiment 8, I used hardware to debounce the button, and I used firmware for a delay. So essentially what we're going to do in experiment 9 is the opposite. We're going to use the timer counter for the delay, which is external hardware, and then I'm going to, somewhere in here, I'm going to debounce the thing in firmware. Okay, so experiment 9, once again, experiment 8, debounce the button hardware. Experiment 9, debounce the button firmware. Experiment 8, use the microcontroller to generate a delay for the display multiplexing. Experiment 9, use the timer counter to generate a delay for the display multiplexing. So it's really it's not too hard of a problem. Conceptually, it's really tricky at first, but I think in the end it's very simple. It's more of a refactoring of the previous program and adding that timer counter into it. And that is it, folks.